Hello friends, I am Adeesh Deshpande from Fergusson College. We started the discussion of group 16 elements. So let us continue with the chemical properties of group 16 elements. So in the last class, students, we saw atomic properties of group 16, then physical properties of group 16, and some of the chemical properties of group 16. So let us continue with the same, that is chemical properties in that reactivity towards halogens. Elements of group 16 form large number of halides of the type EX6, EX4 and EX2, where E is sulfur, selenium, tellurium and X is halogen. So let us first consider hexahaloids. So SF6, sulfur hexafluoride, selenium hexafluoride, ACF6, TEF6. They are formed by direct combination. They are colorless gases. They have Sp3 hybridization and possess octahedral structure. SF6 is exceptionally stable for steric reasons. Stability of the halides decreases in the order F minus greater than Cl minus greater than Br minus greater than I minus. So it's but natural. Size of the halogen also increases down the group, and so this is going to be the order for stability of these halides. So here is the structure of sulfur hexafluoride. So octahedral structure as can be seen. Now let us consider tetrahaloids. SF4, sulfur tetrafluoride, ACF4, TEF4 and TeCl4. These tetrahaloids are formed by sp3 dehybridization. So trigonal bipyramidal geometry, one with one equatorial position occupied by a lone pair. So this is going to be a geometry trigonal bipyramidal structure. It is clearly observed that there are two axial bonds and one of the equatorial bonds contain lone pair. Then dihaloids, SCl2, ACCl2, TeCl2. These dihaloids exist. They have sp3 hybridization and possess tetrahedral structure with two equatorial positions occupied by lone pairs. And these group 16 elements also form monohaloids. Monohaloids are dimeric in nature. That means the two molecules exist together. For example, S2F2, S2Cl2, Ac2Cl2 and Ac2Br2. These dimeric haloids undergo disproportionation and form corresponding tetrahaloids. Here is the example of Ac2Cl2. So 2 Ac2Cl2 gives AcCl4 plus 3Ac. Now upon discussion of atomic properties, physical properties and chemical properties in general, now in the remaining chapter we are going to discuss some of the compounds of group 16 elements. In that the very first is sulfur dioxide. So how sulfur dioxide is prepared? It is prepared by three methods as can be seen on the slide from sulfur. So directly when sulfur burns in air or oxygen, it forms sulfur dioxide. So the equation is given S solid plus O2 gas gives SO2 gas. Then how sulfur is prepared? Sulfur dioxide is prepared in the laboratory. In the laboratory by treating sodium sulfite with dilute sulfuric acid, sulfur dioxide gas is liberated. So here is the equation Na2SO3 plus H2SO4 gives Na2SO4 plus H2O plus SO2. Sodium sulfite gets converted into sodium sulfate. Then how industrially sulfur dioxide gas is prepared? Then it is prepared from sulfides by roasting zinc sulfide and iron pyrites. Roasting is sulfide ore is heated in presence of oxygen. So the equation is given 2ZnS solid plus 3O2 gas gives 2ZnO solid plus 2SO2 gas. Similarly, 4FeS2, these are iron pyrites, plus 11O2 gas gives 2Fe2O3 solid plus 8SO2 gas. So these are the methods of preparation of sulfur dioxide. Physical properties. Sulfur dioxide is a colorless gas with a pungent smell. Pungent means suffocating smell. So if we take a smell of SO2, if we inhale SO2, then it is always a suffocation that we can observe. So colorless gas with pungent smell. Poisonous in nature. Highly soluble in water. So solution in water is called as sulfurous acid. It liquefies at room temperature under a pressure of 2 atmospheres and boils at 263 Kelvin. Now let us consider some of the chemical properties of sulfur dioxide. The very first is reaction with chlorine. So it combines with chlorine in presence of charcoal to produce sulfuryl chloride. So equation is given SO2 plus Cl2 in presence of charcoal, that is carbon, it forms SO2Cl2. SO2Cl2 is sulfuryl chloride. Then second reaction is with oxygen. Sulfur dioxide gets oxidized to sulfur trioxide by dioxygen in presence of vanadium pentoxide as catalyst. So conversion of SO2 to SO3. Equation is very simple. SO2 plus O2 in presence of V2O5 gives a 2SO3. Now reaction with sodium hydroxide. It reacts with sodium hydroxide solution to form sodium sulfite. So 2NaOH plus SO2 gives Na2SO3 plus H2O. And the last reaction is reaction with sodium sulfite. It reacts with sodium sulfite to form sodium hydrogen sulfite. Simple reaction, Na2SO3 plus H2O plus SO2 gives 2NaHSO3, sodium hydrogen sulfite. Then sulfur dioxide acts as a reducing agent in presence of moisture. Moist sulfur dioxide reduces ferric salts to ferrous salts. So, as we studied earlier, sulfur dioxide acts as a reducing agent in presence of moisture. So, Fe3 plus ions are converted into Fe2 plus ions. So, equation is 2Fe3 plus SO2 plus 2H2O gives 2Fe2 plus SO4 2 minus plus 4H plus. So, Fe3 plus ions are reduced to Fe2 plus ions, gain of electrons, and so sulfur dioxide acts as a reducing agent. Moist sulfur dioxide decolorizes acidified potassium permanganate solution. So 2KMnO4 plus 5SO2 plus 2H2O gives K2SO4 plus 2MnSO4 plus 2H2SO4. So if we find the oxidation state of manganese, in KMnO4 it is plus 7 and in MnSO4 it is plus 2. So again Mn plus 7 ions are reduced to Mn plus 2 ions, and so sulfur dioxide again acts as a reducing agent. Then moist sulfur dioxide reduces halogens to haloacids. So simple equation, conversion of iodine, that is I2, to hydrogen iodide, Hi. So I2 plus SO2 plus 2H2O gives H2SO4 plus 2Hi. So I2 has oxidation number 0 and in Hi oxidation state is -1. So again sulfur dioxide acts as a reducing agent. Then the structure of sulfur dioxide. So ground state configuration is 3s2 3p4. In the excited state, one of the 3p electrons is uncoupled and promoted to the vacant 3d orbital. So there is 3p electron pair. This electron pair is uncoupled and electron is promoted to the vacant 3d orbital. Then there is Sp2 hybridization. So Sp2 hybridization gives you 3 Sp2 hybrid orbitals. Then one of that hybrid orbital contains a pair of electrons. Remaining 2 Sp2 hybrid orbitals contain single electron. And this 3p and 3d orbitals, they do not participate in hybridization. So Sp2 hybridized state is shown. Now, sigma bonds between sulfur and oxygen are formed by Sp2p overlap. So p orbital of oxygen takes part in overlapping and sigma bonds are formed by Sp2p overlap. So there are two such bonds. So in the structure you can observe that there are two sigma bonds between sulfur and oxygen atom between two oxygen atoms. While one of the pi bonds arises from p pi overlap and other from p pi d pi overlap. So one oxygen atom and the sulfur atom, there is p orbital overlapping, that is pi bond is formed. Sulfur atomic orbital is 3p, oxygen atomic orbital is 2p. And as can be seen from the hybridized state configuration, with the other oxygen atom, the sulfur atomic orbital is 3d and oxygen atomic orbital is 2p. So that pi bond is called as a d pi p pi bond. So both sulfur oxygen bonds are identical due to resonance. So resonating structures are also shown. So in all, sulfur dioxide molecule is angular. OSO bond angle is 109.5 degrees. The uses of sulfur dioxide. So here are some of the uses of sulfur dioxide, quite a simple part as can be seen on the slide. Now proceeding towards next compound of sulfur, that is called as sulfuric acid. So sulfuric acid is prepared by contact process. So there are total 4 steps. So step 1 is preparation of sulfur dioxide. So sulfur or iron pyrites, when burnt in excess of air or roasted in air, sulfur dioxide is obtained. So both the reactions we saw earlier during the discussion of sulfur dioxide. So this is the step 1 in the preparation of sulfuric acid by contact process, that is preparation of sulfur dioxide. Then second step is oxidation of sulfur dioxide to sulfur trioxide. This step is quite important. In presence of atmospheric oxygen and vanadium pentoxide as catalyst, sulfur dioxide gets oxidized to sulfur trioxide. The reaction is reversible and exothermic. The forward reaction leads to the decrease in the volume. So by Le-Chatelier's principle, it is favored by increase in the pressure and at low temperature. So optimum pressure is 2 bar and temperature is 720 Kelvin. So in this case, once we maintain these conditions, equilibrium is shifted to the right side and maximum sulfur trioxide can be obtained. In step 3, dissolution of sulfur trioxide in sulfuric acid. So sulfur trioxide gas from catalytic converter is absorbed in 98% H2SO4 to produce oleum. Oleum is fuming sulfuric acid. Formula is H2S2O7. So this sulfur trioxide gas is converted into oleum. And last step is dilution of oleum. To convert oleum into sulfuric acid, it is mixed with water to get sulfuric acid of desired concentration. So sulfuric acid obtained by this process is 96 to 98% pure. So here is the equation, and now here is the summary, that is flow diagram for the manufacture of sulfuric acid. So in the first tower, you will observe hot air is blown into the tower. sulfur burns, sulfur dioxide, impure and oxygen, they are obtained. They are passed through first another, that a second tower is of water spray, where washing and cooling is done. Then it is passed through the third tower where concentrated H2SO4 is sprayed and the gases are dried. Then this dry SO2 and oxygen, they are thereby passed through catalytic converter where there is vanadium pentoxide and sulfur trioxide is formed. And the last tower you will observe concentrated H2SO4 is sprayed where sulfur trioxide is converted into oleum. So this is how sulfuric acid is prepared by contact process. Physical properties. Here are some of the physical properties of sulfuric acid. So quite simple part. Then some of the chemical properties. The first is acidic property. In aqueous solutions, sulfuric acid ionizes in two steps. So in the first step, one H plus ion is given out forming HSO4 minus, and this HSO4 minus bisulfate ion forms another H plus ion and SO4 2 minus ion. The larger value of Ka1 means that H2SO4 shows more dissociation into H plus and HSO4 minus ions. So compare corresponding Ka values, Ka1 and Ka2. Greater the dissociation constant, stronger is the acid. So H2SO4 is a strong acid. All of us know this property. The next property is oxidizing property, quite important property of sulfuric acid. Since concentrated H2SO4 gives oxygen on strong heating, hot concentrated sulfuric acid acts as oxidizing agent. So here is the equation. H2SO4 gives H2O plus SO2 plus nascent oxygen. So this nascent oxygen is responsible for oxidizing property. Metals and non-metals both are oxidized by hot concentrated sulfuric acid, which itself gets reduced to sulfur dioxide. So Cu plus 2H2SO4 gives a CuSO4 plus SO2 plus 2H2O. Then S plus 2H2SO4 gives a 3SO2 plus 2H2O, and C plus 2H2SO4 gives CO2 plus 2SO2 plus 2H2O. Then dehydrating property. Concentrated sulfuric acid is a strong dehydrating agent, means it has a very strong affinity for water. So sulfuric acid removes water from sugar and carbohydrates. Carbon left behind is called sugar charcoal, and the process is called as charring. So this is the charring process, C12H22O11. Sugar is taken, concentrated H2SO4 gives you 12C plus 11H2O. So this is quite one of the important property, that is dehydrating property of sulfuric acid. Then reaction with salts. Concentrated sulfuric acid decomposes salts of more volatile acids to the corresponding acid. So some of the equations are given. With sodium chloride, sulfuric acid forms sodium bisulfate. Then with potassium nitrate, sulfuric acid and potassium nitrate forms potassium hydrogen sulfate. And sulfuric acid with calcium fluoride forms calcium sulfate. Some of the uses of sulfuric acid. Sulfuric acid is regarded as a king of chemicals, as it is very important industrial chemical. So it is used in the manufacture of fertilizers like ammonium sulfate, superphosphate, etc. In the manufacture of pigments, paints, dyestuff intermediates. In refining of petroleum. Then in detergent industry. In metallurgy as a pickling agent. So what is pickling? Pickling is an industrial process for removing layers of basic oxides from the metals like Fe and Cu before electroplating, enameling, galvanizing and soldering. So all these processes are familiar to us. So to remove the coat of any oxide, This process is carried out, and for that process sulfuric acid is used. Then in lead storage batteries, so these are the batteries which we always use in our households. So that is one of the important use of sulfuric acid. As we know, sulfuric acid is very largely used in laboratory. So it is a very good laboratory agent. In the manufacture of explosives like nitrocellulose products. So it is because of these uses, sulfuric acid is called as king of chemicals. Then oxoacids of sulfur. Sulfur forms number of oxoacids. Some of them are unstable and cannot be isolated. They are known to exist in aqueous solutions or in the form of their salts. So here are some of the oxoacids of sulfur. The first is sulfuric acid. Formula is H2SO3. Oxidation state of sulfur is +4. So here is the structure of sulfuric acid. Sulfur is bonded with two hydroxyl groups and doubly bonded with oxygen. Then second one is sulfuric acid. All of us know this. Another name of sulfuric acid is oil of vitriol. Formula is H2SO4. Oxidation state of sulfur is +6. So structure represents there is two bonds of sulfur with two hydroxyl groups, and then with the two oxygen atoms sulfur is doubly bonded. Then the next oxoacid is di or pyrosulfuric acid, which is also called as oleum. So formula is H2S2O7. Oxidation state of sulfur is +6. Now just try to observe the structure. Sulfur is bonded with, both the sulfur atoms are bonded with oxygen atoms. So there is SOS bond. Then both the sulfur atoms, they are bonded with one hydroxyl group. So there is SOH bond. And remaining four oxygen atoms. So each sulfur atom is doubly bonded with two oxygen atoms. So in all, these four oxygen atoms, they are bonded with sulfur. So sulfurous acid H2SO3, oxidation state of sulfur is +4. Sulfuric acid, oil of vitriol, formula is H2SO4, oxidation state of sulfur is +6. Di or pyrosulfuric acid, that is oleum, H2S2O7, oxidation state of sulfur is +6. Then the next oxoacid of sulfur is peroxymonosulfuric acid. Remember, peroxymonosulfuric acid. Its common name is Carrot's acid. Formula is H2SO5. Oxidation state of sulfur is +6. Now let's go through the structure. Sulfur is bonded with oxygen atom, SO bond. Then this oxygen atom is bonded with hydroxyl group. So the bond is SOOH. Then on the right hand side you will observe that sulfur is bonded with simply hydroxyl group. And remaining two oxygen atoms, they are bonded, doubly bonded with sulfur atom. Then the next one is peroxydisulfuric acid. Peroxydisulfuric acid. This is also called as Marshall's acid. So formula is H2S2O8. Oxidation state of sulfur is +6. Now going towards the structure, sulfur is bonded with hydroxyl group. So both the sulfur atoms, they are bonded with the hydroxyl group, SOH bond. Then both the sulfur atoms, they are linked together with two oxygen atoms. So bond is SOOS. And then each sulfur atom is doubly bonded with two oxygen atoms. So S double bond O, S double bond O on every sulfur atom. So this is the structure of Marshall's acid. Then the next one is Thiosulfuric acid. The formula is H2S2O3. Oxidation state of sulfur is -2 and +6. So remember, as there are two sulfur atoms, one sulfur atom exhibits -2 oxidation state and one sulfur atom exhibits +6 oxidation state. So going towards the structure, sulfur atom at the center gets singly bonded with the two hydroxyl groups. So SOH bonds. Then with the last oxygen atom, there is a sulfur oxygen double bond. So this central sulfur atom has +6 oxidation state. And now with other sulfur atom, there is SS double bond. So with that second sulfur atom, it exhibits -2 oxidation state. So as both the sulfur atoms are covalently bonded, this is the second sulfur atom exhibiting -2 oxidation state. So these three are remaining oxoacids, that is peroxymonosulfuric acid, Carr's acid, H2SO5, oxidation state of sulfur is +6. Then peroxidizing acid, that is Marshall's acid, formula is H2S2O8, oxidation state of sulfur is +6. And thiosulfuric acid, H2S2O3, oxidation state of sulfur is -2 and +6. So students, in this class, we saw two compounds of sulfur, that is sulfur dioxide and sulfuric acid. We discussed their methods of preparation, physical properties, chemical properties, and uses. And at the end, we studied some of the oxoacids of sulfurs, their names, formulae, and structures of oxoacids of sulfur. So here we completed the discussion of group 16 elements from chapter number 7. In the next class, we are going to start the discussion of group 17 elements. Thank you.